So the practice question is the equilibrium constant for A yields B is 0.5 at 20 degrees Celsius and 10 at 30 degrees Celsius. Assuming that delta H is independent of the temperature, calculate delta H, delta G at both temps, and delta S. So here's what we have. We have that at 30 degrees, so at 30 degrees, KEQ, it's a horrible looking E, but KEQ is equal to 10. At 20 degrees, KEQ is equal to 0.5. So the only two variables we have are temperature and equilibrium. And we're supposed to calculate all of the thermodynamic points. So what we have to start off with is you can start off solving for delta G at both temperatures, which is not a problem. So delta G standard state, and that's what by the way that's what we're doing, standard state. I couldn't get the little zeros in there on this software that I'm using, but standard state, delta G standard state is equal to negative RT times the natural log of KEQ. So for KEQ at 30 degrees, we just plug in a 10, and we plug in for our temperature 303 Kelvin, and R is negative, or as R is 0.008134. So at 30 degrees, delta G standard state is going to equal negative 5.8. And then the same thing, you just change this to 293, you change KEQ to 0.5, and so at 20 degrees, delta G standard state is equal to positive 1.69. So then the next thing is, in order to calculate delta H, remember the Van't Hoff plot where basically what we decided was that delta H standard state was equal to negative R times the change. Well, we would say that it's equal to D, but since we're not going to be finding a derivative, we'll just say the change of the natural log of KEQ divided by the derivative or the change of 1 over T. Now, because on a Van't Hoff plot you get a slope that's slightly curved on the way down, so you're figuring out the natural log of KEQ is being charted against 1 over the temperature in Kelvin. You get a slightly curved slope, so the delta H would be the tangent line that intersects there. And so whenever you have very small distances, you can find delta H standard state just by using the change of the natural log over the change of 1 over temperature. However, if it's large differences, delta H can change slightly as you go up the graph. So what I'm saying is delta H is temperature dependent, but over small distances it's temperature independent. Over small temperature ranges it is temperature independent. So here are the pitfalls with this. So the change of the natural log, let's start with that. So the natural log, it starts out at, so the final natural log, the final equilibrium constant is 10, and so final minus the initial equilibrium constant was 0.5. So it is not the natural log of 10 minus 5. It is not that. It is the natural log of 10 minus the natural log of 5. So it's the change of the whole natural log. And so the natural log minus a natural log is the same as the natural log of 10 over 5. If you don't know what I'm doing here, go back to your algebra class and learn that. And so it's the change of the natural log of 10 over 0.5. And I put 5 there, but it's 0.5. So there's the number here. And so we get it's equal to the natural log of 20. So the natural log of 20 is our numerator. Now the change of 1 over t. So here's what the mistakes you're going to make with this. Somebody's going to put the change of 1 over t is equal to 1 over, what was the first temperature? It was 30. So 1 over 30 minus 20. So they're going to think it's 1 over 10. That is not the case. Or you may have converted to Kelvin, which you need to convert to Kelvin, but you would have said the 1 over 303 minus 293, which you still get 10, and that's not the case either. The change is not the change of 1 over the change of temperature, so it's not 1 over the change of temperature, it's the change of 1 over the temperature, the whole thing. So 1 over 303 minus 1 over 293, so 293, 303, 293. So let me move some stuff out of the way so we can continue. And I wonder if it'll let me. Alright, so what we have now is negative r. So negative 0.008314 times the natural log of 20 over. Now this number is negative and it's fleetingly small. So 1 over 303 minus 1 over 293 is negative 1.12 times 10 to the 4th, 1.1263925 times 10 to the 4th, 10 to the negative 4th, beg your pardon. So when you multiply out, you're going to get a negative number right here, and then you have your negative number right here. So you're going to end up getting a positive. The delta H is positive 221, approximately 221.11, something like that. And if we're assuming that it's temperature independent, then it's not going to change whenever we go from 20 degrees to 30 degrees or back and forth. So at this point we can calculate delta S. We know that delta G, standard state at, we'll just start at 20 degrees, is equal to 1.69. And so delta G standard state, this is horrible, delta G standard state is equal to delta H minus T delta S. And if we just solve for delta S, we get delta G standard state minus delta H standard state divided by negative T is equal to delta S. So you just plug in your numbers. So for delta G we said 1.69, and we're subtracting off delta H, which we said was 221. And we're going to divide by negative T. Well, at 20 degrees, negative T would be negative 293 Kelvin, and so that should equal approximately 0.748, and I think 0.7484. But basically, because I've rounded on my temperature, I didn't use 273.15 as my conversion factor. You could actually just go ahead and round this to 0.75 and call it good. So delta H is equal to 0.75, and make sure your units are in kilojoules and not joules, because usually delta S is in units of joules. So kilojoules per Kelvin times moles. And that is the answer. And so it actually does change by like 1/10,000th of a unit if you calculate it at 30 degrees. So delta S does change, but it's so fleetingly small. It's less than 1 part in 1,000. And so it's basically when you round to the 100th place, you still get the same answer.